Good afternoon, students. Welcome on this live session. As this is our first live session on the spectrum communications and jamming course, I wish to actually start initially with the fundamentals of this course, what we have discussed till now on the course. Through this last 28 modules that is already been telecasted, and you are going through all of them. I hope you are also enjoying the tutorial session and nicely following all those tutorials. We have started receiving your assignments, and their responses are really good, and the responses are really impressive. I know that this week you have started giving the feedback on the MATLAB codes. It is I am very happy to see some of you are trying to write your own codes and trying to implement the typical systems and the code generation mechanisms that we are teaching online. To start today's live session, let me give you a brief what we have already been discussed online on the fundamental of the spectrum communications. Remember, as I have already discussed, that spread spectrum is something dealing with the design of the waveforms to improvise security in the physical layer modem design. When I tell it is a modem design, it means the transmitter plus receiver design. Basically, security in these days in the design of a telecommunication system, improvising security is the utmost important thing. Traditionally, it was very important criteria for designing of the military communication systems. But these days, as we have progressed for the very high data rate communication from 3G to 4G and migrating slowly towards the 5G communications, security has become a very important issue to be incorporated in all the layers of the communication system. When I talk about all the layers, it involves really the all 7 layers of the OSI. Earlier we used to give the security only from the higher layer by means of the encryption or some means of the network coding. I hope you have heard about these terms. Whereas, in contrast to that, spectrum communication provides the security in the physical layer itself. As the name is suggesting, we are playing with the spectrum itself here. You are spreading the spectrum of the signal and improvising the security against the jammers. So, as a whole, that is the main explanation of the main terms of this course: spread, spectrum, communications and jamming. In this course, not only we talk about how to improvise the security against jamming, we also improvise the crucial points how a jammer thinks. Actually, it is the course also talks about the intuition of the way the jammers think. Actually, the original communication signal can be jammed when the communication is going on the air. So, as you are playing with the spectrum itself, so spread spectrum talks about, as I told, that we are spreading the original bandwidth of the data signal more than it is bare minimum required. For example, if I tell that you are designing a BPSK modulation system and I have given you a 1 megahertz bandwidth, it is intuitive that with 1 megahertz bandwidth using BPSK modulation scheme, I can actually develop a system which can give me a 1 megabit per second data rate. This is how the calculation comes. Calculation comes straightforward, that BPSK in one carrier 1 bit per second can be sent. If I have a 1 megahertz bandwidth, that means that I can transfer 1 megabit per second. So, if I give you a higher modulation scheme, for example, QPSK, you have 2 orthogonal carriers. So, same 1 megahertz bandwidth, using the same 1 megahertz bandwidth, you can double your data rate. So, earlier I was transmitting at the rate of 1 megabit per second, now I will be able to transmit at the rate of 2 megabit per second using the same bandwidth. That is the usual way we design the modulation and we design the high data rate communications system. So, if I now say that suppose to transfer my data, I need minimum 1 megahertz per 1 megahertz bandwidth to transmit 1 megabit per second using a BPSK modulation scheme, and suddenly I am transmitting the same data rate over a suppose 5 megahertz bandwidth. So, traditional communication system will transfer 1 megabit per second data rate using BPSK say over 1 megahertz. The same data rate will be achieved in the spread spectrum communication using 5 megahertz bandwidth. So, fundamentally you understand that we are by means of some technique we will be using it, but definitely we are using more bandwidth than the bare minimum required for transmitting 1 megabit per second using BPSK. This extra 5 times bandwidth that I have talked as an example, this extra 5 times bandwidth will be utilizing to spread your signal so that some kind of security can be improvised. How will you spread this it may be different. The different types of techniques that we use here, sometimes we call it a direct sequence spread spectrum, sometimes we call it frequency hopping spread spectrum, sometimes it is a hybrid spread spectrum communication technique compromising or amalgamating the direct sequence spread spectrum with the frequency hopping spread spectrum. It may be sometimes a time hopping spread spectrum purely also. Question may comes that at which situation which kind of the technique I will be using. Definitely actually there are the advantages and the disadvantages correspondingly for each and every kind of the spread spectrum communication technique. For example, direct sequence spread spectrum communication technique is a very famous one and mostly used techniques in the military communication modem designs. Remember another thing, I took an example of 5 times increment of your spread spectrum communication technique. This 5 times increment if you wish to do, definitely you have to do it by the amount of term that we call a processing gain. This gain basically is a measure of how much time you are increasing the extra bandwidth than the bare minimum required. Now, the question starts from here, that how this increment of the or spread of the signal, am I allowed to go ahead with spreading the signal infinitely. For example, instead of 5 times increment, can I go about 500 times increment? Because remember, whenever you are spreading the signal than the bare minimum one required, definitely actually you need that much wider bandwidth for transmission. Fundamental question comes that where from you will get that extra bandwidth, and how then in the practical system we are going to implement the system design. There is a catch. Catch is that the channel bandwidth is a priori given to you. When we start designing some spread spectrum communication system, we first take the input, what is the available channel bandwidth. Channel bandwidth means the wireless channel bandwidth that is given by a particular technology worldwide allowed for designing a typical system. So, if your channel bandwidth available is suppose 500 megahertz, then that is the maximum spread bandwidth that you can play with. Now, the question starts like this: if my bare minimum bandwidth that is required, how I will select that bare minimum bandwidth? It depends again upon actually what is the minimum data rate support required for your transmission for a typical system. It may happen that the system that I am designing, the bare minimum data rate that I need to support is suppose 100 kilobit per second. That requirement will come from the customer directly. What is the bare minimum data rate we need to support? So, 100 kilobit per second is the bare minimum data rate that I need to support, and I have to support suppose up to 1 megabit per second in that system. I have 500 megahertz bandwidth with me. So, lesser the data rate, smaller will be the bandwidth requirement if I do not change my modulation scheme. And then the processing gain, the scope, how many times or how much time I can spread my signal over the whole 500 megahertz bandwidth, that varies. Higher the data rate, the scope of the spread is less, lower the data rate, the scope for spreading the bandwidth is more, keeping that the total available, final available channel bandwidth is fixed. So, this factor processing gain, which actually is the heart of this design, which is basically telling that how much time you will be spreading the signal, that processing gain is calculated in different spread spectrum communication system in different way. For example, in a direct sequence spread spectrum communication system, where a signal is multiplied with a very small duration chip sequences, and where actually the sequence duration is basically very low than the duration of your data signal. That is shown in one of the slide sets of the direct sequence spread spectrum communication system here. There the gain is directly calculated by dividing the Ts, which is the signal time, divided by Tc, what is the chip time. Remember, this Ts by Tc, you should be choosing the Tc in such a way that Ts by Tc gives you the processing gain, and that gain will never spread the bandwidth that is available finally in your hand. Okay. This is a straight way, the way we calculate here the processing gain for a direct sequence spread spectrum. There is another question. So, this chip, how many chips will come, that depends upon how small you are choosing your Tc. So, within the time dA, within a time of the data signal Ts, the number of the chips that are coming, that is also a calculation of the processing gain directly in that sense. Remember another thing, that the length of the sequence is equal to the number of the chips that are coming within the time period Ts. So, smaller the Tc is, more number of the chips are expected to come within that duration of your data Ts. Now, the length, this number of the chip basically telling us what will be the length of the sequence that you are now dealing with. So, choice of this length versus the spread given actually channel bandwidth and understanding the lower minimum data rate that I need to support is a complete design problem. Now, another good part I should say here, for spreading the sequence in spread spectrum communication, you need this code. The code that now I am talking, this is a chip, the PT in this slide. The code length is a typical design parameter that I have already mentioned. Remember, more the length of the code will be, more it will be difficult for any jammer to understand or to hack the code. That is why actually there is a trick that we always try to prefer the larger length codes in a spread spectrum communication. If the length is really very high, it means that you can provide more security in your design system. But if your length is really very high, that means actually the processing gain also it may be high, but fundamental bandwidth of the signal that is slowly reducing. The effective bandwidth, original raw bandwidth of the signal with which you are starting, that has to reduce, because see the processing gain gives actually the final bandwidth divided by the original bandwidth. So, more and more actually the original bandwidth requirement is, less chance will be to spread, how many times I am spreading. If the time factor that is smaller, that directly affects the length of the code you are designing. More the processing gain, more will be the length of the code. And thus, if your code design is not having the larger length, then the security is also on time. So, there is another pillar, I should say the constraint to design such system, where it is also asked that how much data rate you can sacrifice, so that more security I can improvise. If the lesser data rate you will ask for, more actually I can give you the security, because the length of the code that I will design now, it will be increasing. And it is intuitive also that for a jammer, it will be very hard for him to crack a very long length codes. So, you will use for the GPS very long length codes, which is actually spread over 7 days. If you see the timing of a GPS code, it will be spread over 7 days. So, the code also changes, keeps on changing at some frequency, but can you break a code whose length is spread over almost 7 days? So, that is another extreme example I have given. Usually for other communication systems, with the length of the codes that we use, sometimes it goes even actually up to your 256 or 1024. A very common kind of the codes that we use for such communication systems are the M sequence code, which is mother of all codes that we generate. We also sometimes use the codes like Hadamard code, Kasami code, Gold code, orthogonal OVSF codes. Out of all this, Hadamard, Walsh Hadamard, Kasami, they are actually really well used codes. Remember, when I will say that it is a very good code, what do you mean by a good code? Not only that, actually the code that will give me the highest security. It is also a code will be always considered to be a good code if the autocorrelation property of the code as well as the cross correlation property of the code simultaneously is really very nice. When I say autocorrelation property is very good, it means when I do the autocorrelation, the peak appears at very sharp and the side lobes power of the autocorrelation profile is very low. But when I talk about the cross correlation property, I understand the cross correlation should be always close to 0. So, fortunately or unfortunately, in the history of the code design, we could not design a code which has simultaneously a very good autocorrelation as well as very good cross correlation property. You may ask the question, why do I need simultaneously a code which has a good autocorrelation or good cross correlation? because my receiver knows what code is getting used in transmitter. So, I will display my signal sitting in the receiver with the same code. So, autocorrelation property, if it is very good, I can detect my signal, but for the cross correlation, why I am asking that the cross correlation also needs to be very, very good. What do you mean by a cross correlation is, suppose I have given you a code whose length is 32. So, a 32 length code when we design, suppose it is a Varshadamat code. So, definitely I can generate same time I can generate a capital L minus 1 means 32 minus 1, 31 number of 32 length codes. We call it all will be Walsh-Hadamard codes only, and all of them will have a property where the cross correlation properties are expected to be very low. What I mean to say is, see, I have a 32 length code. From that 32 length code, I can generate another 31 number of the codes, and this is constituting a set of the codes, and all those codes will be having a cross expected to have at least the cross correlation property is extremely low. Cross correlation means, suppose code number 1, if it is cross correlated with the code number 7. So, whatever the values at the output we will be getting, that values should be close to 0. Why am I asking this? Because think of a wireless situation. In a wireless communication scenario, there won't be a single transmitter and single receiver, right. There will be always a multiple transmitter and receiver simultaneously operating. If everybody in that technology using a spread spectrum communication technology, so you need to understand, and suppose they are the multi users and all of them suppose are transmitting at the same time to a particular station. So, each and everybody has that independent data, and they should spread their individual signal using a unique orthogonal code. So, if I am having 32 length code and such 32 length code I am telling I am having 31 in number at a time. So, it is intuitive, all the 31 different codes I can give to 31 users. So, that simultaneously 31 users can transmit their data to a center point, provided all these 31 codes are orthogonal to each other. Then nobody will interfere each other's data transmission, and nobody also can infer the information of the others also. You need to know actually who is using which code, otherwise nobody can do it. But at the center where all the users data are reaching, he understands that what different codes, orthogonal codes are given or getting used by which user. So, he has the complete map. He knows actually that which code is getting used by which user, if the protocol can be designed like that, but the users they do not know. At the same time, the jammer, if any jammer is coming and he wishes to jam the signal, he need to know that which code is getting used by which user to jam a particular user's transmission. So, there are twofold security in that sense. I mean, more actually the length of the codes, more actually you can give the security, more orthogonal set of the codes at a time will be getting generated if the length of the codes are high. Hence, more number of multiple user communication is possible to support at the cost of definitely a lowering data rate. So, in that sense, the designing of a code is the heart of this spread spectrum communications. I can hack the signal, I can jam the signal only if I know which code a user is using to spread his signal. So, as I have told that hacking will be very tough, very much tough if I am using a long length codes, that is one issue. Apart from that, how can you make the hacking to be very tough for the user is, if I am using code can be actually real valued and chips, I mean to say. For example, in this slide you are seeing the values that the chip is picking up is the +1 and -1 only. So, the values are real valued. Otherwise, the chip can also be having a complex valued. If it is real valued, so following a digital communication, the values may be either 0 or 1 or it may be +1 or -1. So, all real valued codes that we have designed in the history of communication, the real valued codes are either having a +1 value or a -1 value. The codes are varying from each other in terms of the autocorrelation and cross correlation, and how these +1s and -1s are coming, that is the meaning. But when I am talking about a complex code, these chip values will be complex numbered. So, for a jammer or a hacker, it will be really another level of travel to hack your code if you design a complex valued code. So, there are two tricks here I have told. You make the code length very long, it will be hard for the jammers to hack you. Again, you can make them a complex valued code. We call it something a linear sequence and a non-linear sequence also. So, linearity and non-linearity is a method that we also sometimes improvise to bring the security more and more. What do I mean by linear and non-linear? So, in the code generation mechanism, if you see, already we have discussed the course in the module that how to generate a PN sequence code. PN sequence code generation happens by means of some flip flops. So, you have a set of the flip flops where actually for every clockwise the signal proceed and one by one the bit is generated at the output, and from the output to the input we send a feedback. This feedback can be linear. For example, to output of any two flip flops, I can have a XOR gate simple added, the addition of that output I am feeding, or very simple way any one of the output of the flip flop also can be fed back as a feedback. So, sometimes if there is a linear equation in the feedback path, we call it the linear kind of the code are expected to generate. Think of a situation, if I generate a sequence such a way that in the feedback path I have applied a multiplexer, I have added the combination of two combinatorial circuit, output of that guy is coming as a feedback to my input, then design of the feedback itself is improvising another level of security. So, hackers may assume that how many number of the flip flops you might have used, seeing if he can assume the length of your code, it is easy to do that. But if your feedback mechanism is very much complex one, then it is very hard for him to understand how you might have done the feedback, and depending upon the way you have done the feedback, the sequence that you are generating at the output of the code, it keeps on changing. So, lot of intelligence you can improvise by changing the feedback path design. Sometimes people do that the feedback path itself will be driven by another code generation circuit, and that will be generating a sequence. According to that sequence, the feedback will be coming out. So, there are a lot of way that people have thought of and people have designed the whole feedback part to improvise actually new intelligent code designs, which we call non-linear codes. So, in gist, how you can increase the security is by increasing the length of the codes, by improvising the non-linearity in the feedback path or non-linear codes. Sometimes we use complex valued codes also for spreading the signal. Compared to your real valued codes, the application of the complex valued codes in the practical system design is very less, but implication of the nonlinear codes are there. So, understanding that this code design will be the heart of this whole space spectrum communication system, one point I should mention here that remember, whenever I am talking about the code design, there are standard codes already available, and orthogonality in the set of the generation of the codes basically actually is hold for satisfying such kind of the system designs. Remember, actually when we have designed the direct sequence space spectrum system, applied it for the cellular communication in the CDMA, code division multiple access, which was actually heart of the 3G communication system. There actually to support a huge number of the multiple users, that is obvious in any kind of cellular communication system, huge research already is being done to generate this set of the orthogonal codes. So, if you search in some literature, you will find that how to generate the set of multiple set of the orthogonal codes is really a big research area that people have done over the years, and also come up with the very good set of the orthogonal codes. So, getting multiple set of the orthogonal codes is a very hard and tough task to go ahead with. And we could not really do with the perfect orthogonality among the users in a cellular communication in the CDMA. We have done the partial, we have utilized the codes where actually the pretty good amount of the orthogonality is maintained, but not perfect orthogonality for all the users we could maintain in such situation. So, whereas in the military communications where the users were less, so small length codes like 32 or maximum 64, we could design the good military communication system with very high security. Now, the question comes actually where this kind of the space spectrum communication systems have been used in practice. One example I have told in the military communications, traditionally over the years we have used. The second point is in the cellular communication in CDMA, WCDMA, 3G communication systems we have used it. Third use was the Wi-Fi communication. When Wi-Fi came up, IEEE 802.11 standard, the first generation of Wi-Fi when it came up, even actually the second and third generation of the Wi-Fi, when 802.11b, 802.11a, such standards were there, and the devices are still there in practice. When they came up, that time when the Wi-Fi started, they initially started with the support of a single carrier communication system with direct sequence space spectrum communication. They supported up to 11 megabit per second data rate only when the channel bandwidth was 25 megahertz. Remember, I was giving a support of 11 Mbps only, but the channel bandwidth was 25 megahertz. And in their cases, there was a lower limit where they have supported only 5 megabit per second, but the available channel bandwidth was 25 megahertz. So, they usually got a chance of spreading the signal at least 5 times, 2 to 5 times, depending upon the data rate target. And when they were doing that, they have implemented these same direct sequence space spectrum communication system in Wi-Fi. So, if you have any question understanding that why am I studying this subject, is there any practical use of it? Answer is yes, there are several use cases over the years people have developed, the devices are in use, the technology is in use. And this technique is also getting improvised in some of the use cases where actually this 60 gigahertz based communication system is coming up for future generation communication for the Wi-Fi only. There is a standard already been frozen by IEEE, which we call 802.11 AD. This is a standard which gives us a possibility of transmitting in a short range using 60 gigahertz frequency. And there are variety of the data rate support requirement. For the small data rate requirement, for example, if it is a IoT based small cell networks, IoT based industrial IoT network, where the data rate support requirement is really very small, there we have utilized the spread spectrum communication system based very low power energy efficient and system design for IoTs using this 60 gigahertz communication, where direct sequence spread spectrum communication is utilized. Apart from here, if you look into the military communication systems, till today in our country and worldwide, the military communication systems are spread spectrum based only. They do not trust only on the encryption, they trust mostly on the physical layer, improvising security that is done here. But in the military system, slowly they are migrating from direct sequence spread spectrum system to the frequency hopping spread spectrum system. The basic difference between direct sequence spread spectrum and the frequency hopping spread spectrum system is, here you multiply data sequence with a shorter chip sequences, and as you are after multiplication, your data sequences become equivalent timing that of a chip. So, in the bandwidth, in the frequency domain, the bandwidth expands. But in the frequency hopping, what you do? In the frequency hopping spread spectrum communication, you hop over the multiple frequencies. For example, if I give you a 25 megahertz bandwidth, you divide that 25 megahertz bandwidth suppose by the 5 division. So, at the end of every 5 megahertz, suppose you have one channel. So, what I have done? I had a 25 megahertz channel given to me, divided it by 5. So, I have 5 channels. Each channels are having a bandwidth of 5 megahertz. Now, I will design a code. That code will tell that sometimes the value is 1, sometimes the value is 5, sometimes the value is 3, sometimes the value is 4, sometimes the value is 2. So, whatever the value that code is telling, based on that, symbol by symbol basis, my symbol will be transmitted any one of these channels. One easy way of understanding is, I have the QPSK modulated symbols, for example, I have to transmit. Question is, at which frequency I will transmit? I told you have 5 channels. So, you have 5 options. Either you can transmit on channel number 1 or channel number 2 or channel number 3, channel number 4 or channel number 5. Now, the easy way is you can do one by one. The first channel is first symbol is transmitted over the first channel, then followed by the second, then third, then fourth, then fifth. If you do that, it will be very easy for any jammer to observe what is going on for a certain period of time and hack you. But now, if you design a code, with the code will tell at particular moment on which channel you will be, then definitely it will not be that easy for the jammer to understand how you are hopping over the channel to transmit your symbol. So, if I am having more number of the channels, more number of the hoppings I can do, it will be more tough for the jammer or the hacker to jam or hack me. That is the simplest funda. And now, more number of the channels I can really create. If I create more channels, the bandwidth of each of these sub channel, that is reducing. I hope you are understanding that. So, 25 divided by 5 will give me 5 megahertz channel, but 25 divided by 25 will give me 1 megahertz channel only. I can go either I will divide my channel by 5 or 25, that depends again on what is the fundamental band data rate that I have to support. If my fundamental data rate is below 1 megahertz, definitely I can get 25 channels over a 25 megahertz bandwidth, and then I will nicely hop over all these 25 possibilities, and how, in which pattern I will hop, that pattern will be generated by my code. So, this code generation here, the length of code again is coming in the frequency hopping spread spectrum, but the length of this code is again now a function of the available number of the sub bands or sub channels that you are dividing. Remember, there is no fixed rule that you have to have either 25 channels or 5 channels or 10 channels. From design to design, from system to system, it varies, and it is a design parameter. Given the minimum data rate support you have to do, given the total bandwidth over which you can spread your signal, given the how fast you need to move, based on all that we design a typical code, and hence more the number of the channels will be, more I have to have the length of the codes. Why is it so? Suppose I have 7 number of the channels. So, I need to understand, I have to identify 7 channels explicitly. What is the length of the code I need? Then length of the code I need is 3 only, because 000 to 111 if I can generate. So, automatically I can separate out 7 discrete sub channels, but if I give you 25 sub channels, so you need to increase the length of the code, so that you can discretely segregate from 0th channel to 25 channel. So, like this way, I mean, more number of the channels are, your length of the code is continuously increasing, and more the length of the code is, more the security is getting improvised in the frequency hopping also. But again, like the direct sequence spread spectrum communication, in the frequency hopping spread spectrum communication also, the fundamental point below which you cannot come down in terms of the bandwidth is governed by the minimum data rate support requirement given by any system design. In the whole course, once we will progress, you will see that apart from understanding this different kind of the spread spectrum communication technique, we will be also design of the different kind of this code generation mechanisms. We have also discussed little bit about the Galois field mathematics. Galois field mathematics needs to be understood to understand what are the philosophy of designing such codes. Galois field mathematics easily tells us that how the correlation properties of this different kind of the set of the codes, how actually should be improvised. How we choose the polynomial from where, the generator polynomial from where the codes will be slowly generated. Galois field mathematics is little bit different than the way our linear algebra or our general mathematical courses we have learned since our childhood. The way we understand addition in our normal mathematics by means of adder, we do not understand it is in the same way in the Galois field. For example, a simple arithmetic addition in your normal mathematics will be replaced in the Galois field by an XOR operation. Similarly, multiplication, division, everything will be seen in the different way in the Galois field mathematics. And the way we write the polynomial for generation of the codes, it will be governed by the addition, subtraction, multiplication or division of the Galois field only. That won't be a simple arithmetic addition, subtraction, multiplication or the division of the normal arithmetic. Please follow the Galois field mathematic modules very nicely, and we have also suggested there the book that you can support or you can look into for getting details on the Galois field mathematics. So, the third important part after Galois field mathematics that we will be discussing here is the interception, the methodology of intercepting, and finally, the design of the different detectors. Very important thing is that we have split the signal, understood, in the transmitter. Receiver knows the code, so he can disparate. But what about the detectors? Can any simple detector that we use in a normal communication system, for example, the traditional communication systems, can they be directly used for space spectrum communication? If they can be used, is there any need of changing the detector architecture? That is another interesting part to explore and to discuss. That also we have done in the course, slowly you will learn, I hope. And it was really nice to get all of your questions in the forum. I have already addressed them. One or two questions were not clear as such. I request the people to put the questions once again with a better clarity, and always whenever you are putting some question in the forum, please refer the module or the lecture, and also the point exactly the timing is given. So, you can put also the timing, exact time, which slide number you are questioning on or exactly which one you are not understanding. I will be really happy to answer and clear all your questions in the forum till the next session is coming up, and it will be really great if you also put some queries. Keep yourself ready to put some queries during this live session. I would like to introduce you one of the TA of this course, Ms. Ryan. So, he is taking a lot of load on understanding the queries that you are putting in the forum, and he is also keeping me informed about the queries and detailing the queries and trying to whatever answer I am giving, posting them in there. And he has also taken a lot of load in translating the transcripts that you are hearing as well as you are seeing on your screen. So, not only me, apart from Srayan, also Preeti Priya is there. Today she is not here, most probably the next session she will be there. I will introduce her also with you all. So, thank you all, and let us wait for the next live session. Till that point, we will be keeping contact over the forum.